Figure 1 shows a student walking on a carpet. The student becomes negatively charged because of the friction between his socks and the carpet. Explain why the friction causes the student to become charged. So this is 2 marks. We need to have 2 really clear points about why the student becomes negatively charged. So we need to understand that in order for them to become negatively charged, there needs to be a transfer of electrons. This is because electrons are negatively charged. We also need to understand for our second point that this transfer happens from the carpet to the boy. Before this transfer, the boy was neutral. He had no charge because we know that atoms are neutrally charged. However, after this transfer, the electrons have been rubbed off from the carpet to the boy. So our first mark is saying that there is a transfer of electrons, and our second mark is saying that this occurs from the carpet to the boy. The student's head is represented by the sphere in figure 2. The student is negatively charged. The arrows show part of the electric field around the student's head. Draw 3 more arrows on figure 2 to complete the electric field pattern. So, the first thing that we need to understand when drawing an electric field is that if the field around the object is the same, which we're assuming it is in this question, the lines need to be equally spaced out. If we drew them and they weren't equally spaced out, this would indicate that there is a change in the strength of the field. However, in this case, the field is the same all around the object. Therefore, to draw 3 more arrows, we want them to be equally spaced out around the body, like so, and so they're perpendicular. Then we need to think about what direction does the arrow go in. So when we're looking at electrical field patterns, what we're describing is what would the path of a positively charged particle be in this field. So we know that due to electrostatic attraction, negatively charged particles and objects are attracted to positive charged particles. So this particle would move towards the body. Therefore, we draw the arrows inwards, like so, pointing towards the body. Also, the fact that the line that is drawn at the top that they've already given us, the fact that that is pointing inwards does also indicate to us that the other 3 lines on the body will point inwards, but it's just really good to understand why this is. The negatively charged student touches a metal tap and receives an electric shock. Explain why. So this is an explain question. That means we need to add more detail than if it was a state or a describe question. So firstly, we've got this negatively charged student who's touching a metal tap. And we need to understand that this tap is earthed, so it is at 0 volts. It is also a conductor, as metals are conductors. So we have the metal tap, which is at 0 volts, and we have the negatively charged student. They have a buildup of electrons on them. This means that they are not at 0 volts. Therefore, there is a potential difference between the negatively charged student and the metal tap. So we know that when we have a potential difference, this allows a current to flow. And this current is the flow of electrons from the negatively charged student to the tap, which conducts these electrons. And for our final point, we need to mention that this means that the charge has been earthed. This means that the charge has moved from this negatively charged body, the student, to the earth. So the student has been discharged, or their negative charge has been gotten rid of. Some carpets have thin copper wires running through them. The student is less likely to receive an electric shock after walking on this type of carpet. So, copper is a good conductor. Therefore, what's going to happen is instead of the electrons flowing from the carpet to the student, it's going to flow through the copper wires instead. Because there is less electrons flowing through the student, this means that the potential difference between the student and the carpet is less. We know that potential difference allows a current to flow, therefore there's a smaller potential difference. It will not be large enough for a current to flow. Therefore, they will not receive an electric shock. A teacher uses a Geiger-Müller tube and counter to measure the number of counts in 60 seconds for radioactive rock. The counter recorded 819 counts in 60 seconds. The background radiation count rate was 0.3 counts per second. Calculate the count rate for the rock. So when we're asked to calculate the count rate, what we need to calculate is the counts per second. And what they've given us here is the data 819 counts in 60 seconds. Therefore, if you want to calculate the number of counts per second, we need to do 819 divided by 60. Now this gives us 13.65 counts per second. And they've also given us the background radiation count rate. So we use this piece of data and we minus this from 13.65. And we do this because the overall count rate that we've recorded is 819 counts per 60 seconds. This includes both the count rate from the radioactive rock and the background radiation. Therefore, what we need to do is minus 0.3. So 13.65 minus 0.3. That gives us 13.35 counts per second, like so. A householder is worried about the radiation emitted by the granite worktop in his kitchen. 1 kilogram of granite has an activity of 1,250 becquerels. The kitchen worktop has a mass of 180 kilograms. Calculate the activity of the kitchen worktop in becquerels. So, BQ, becquerels, is a unit of the activity of a radioactive source. So they've told us that for 1 kilogram of granite of this material, the count rate is 1,250 becquerels, BQ. Therefore, this man has 180 kilograms, what we've done to get from here to here, multiplied by 180. So we're going to do the same because the count rate will also increase by the number of times that the mass is increased. So times this by 180, we do 1,250 multiplied by 180, and we get 225,000 becquerels. The average total radiation dose per year in the UK is 2 millisieverts. Table 1 shows the effects of radiation dose on the human body. So here we're given a table with radiation doses in millisieverts and on the right with the effect that they have. As the radiation dose increases, the effects get worse and worse. The average radiation dose from the granite workshop is 0.03 millisieverts per day. Explain why the householder should not be concerned about his yearly radiation dose from the granite worktop. 1 year is 365 days. So we're asked to explain why they don't need to be concerned about the yearly radiation dose, but notice we're only given the dose from the worktop per day. So in this question we need to first calculate the dose that the user will get per year, and then because it's an explain question for the second mark, we then need to say why this value that we've calculated means that they don't need to be concerned. So to calculate the yearly radiation dose received from the worktop, we do 0.003, which is the daily dose, multiplied by 365, the number of days in a year, and we get 1.095 millisieverts, which is little m and then SV. So then for our second mark in this explain question, we need to say, why does this mean that the householder does not need to be concerned? So if we look up to the table again, we can see that 100 millisieverts is the lowest dose with evidence of causing cancer. And what we can notice about the value that we've calculated is this is significantly less than this value, which even hints at causing some serious illness. Therefore, we need to say that the value we've calculated, the yearly dose, is significantly less than the smallest amount required to cause serious harm. Bananas are a source of background radiation. Some people think that the unit of radiation dose should be changed from sieverts to banana equivalent dose. Suggest one reason why the banana equivalent dose may help the public be more aware of radiation risks. So this is a 1-mark question, we just need one reason suggesting why it could be helpful to people to change the units of radiation dose from sieverts to banana equivalent dose. And what we need to get at here is that the banana equivalent dose is much more relatable for people. It's a lot more simple to understand a radiation dose in terms of a banana, which is kind of understandable and in everyday life, in comparison to sieverts, which a lot of people wouldn't understand what this means in context. So yeah, it's easier to compare the banana equivalent dose to something that people are aware of in everyday life, whereas sieverts is more difficult for people to understand. A student investigates how the resistance of a piece of nichrome wire varies with length. Figure 3 shows part of the circuit that the student used. Complete figure 3 by adding an ammeter and a voltmeter. Use the correct circuit symbols. So this is a 3-mark question. We're going to get the first mark for using the correct symbols for an ammeter and a voltmeter, and then 2 more marks for putting those in the correct place in the circuit. So if we look at the experiment that we're doing, we're changing the length of this nichrome wire here and seeing how does this affect its resistance. So we need to understand that resistance R equals V over I, voltage divided by current. Therefore we need a voltmeter in order to measure the voltage, and we need an ammeter to measure the current. So that's why we need those 2 components in this circuit that they've given us. So the symbol for an ammeter is just an A in a circle like so, and then the symbol for a voltmeter is AV in a circle like so. So when we're talking about current, we talk about the current through a component. And what we need to do to calculate the current through this wire that they've given us is just put the ammeter in series. So in series just means at any point along this wire would be in series with the nichrome wire. So for example, I could put it here, just draw an A, this is my circuit symbol. But for example, it could also go here, it could go here, it could go anywhere on this circuit, and that would still be a correct answer. And now for the voltmeter. When we're talking about voltage, we talk about, or potential difference, we talk about the potential difference across a component. So when we're talking about potential difference, we're talking about the potential difference between 2 points. For example, these 2 points on either side of the wire. We're talking about the difference in energy transferred per unit charge from this point to this point. So we need to put our voltmeter in parallel with our component. So that looks like this. Describe how the student would obtain the data needed for the investigation. Your answer should include a risk assessment for one hazard in the investigation, and this is a 6-mark question. So you might get 1 or 2 of these 6-mark questions in your exam paper asking you to describe a practical. So what we need for this 6-mark question is to clearly answer the question, which is how would we obtain the data, And this also needs to be written out very clearly and in a logical way in order to get those full 6 marks. So first, just to provide some understanding of the practical. What we're doing is we are changing the length of the wire and we want to see how this affects the resistance. So if we were to draw a graph, we would have length on the x-axis, that's measured in meters, and then we would have resistance on the y-axis, and that is measured in ohms. So as we change the length, which is our independent variable, is what we are changing and seeing its effect on the dependent variable, which is resistance. We're measuring this to see how it changes. So what we need to do is talk about how we obtain the data, which allows us effectively to draw this graph. So what we need to notice is that resistance R, as mentioned in the first part of this question, equals V over I, because what we're measuring is the voltage and the current. So we need to discuss, firstly, how we take the voltage measurements, how we take the current readings, and then how we use these to find the resistance of the wire at each length. We also need to discuss what apparatus we use at each stage in order to make the measurements. So then we need to talk about the how we can improve the accuracy of our investigation. And most often we do this by taking repeat readings. What we do is, for example, with this, we would unplug the circuit, we would take, we then plug it back in, we would take a current reading and we would take a voltage reading. Then unplug the circuit, take another current reading and another voltage reading. Then unplug it, plug it in again, take another voltage and a current reading. We would then have 3 readings, 3 current readings, 3 voltage readings. As long as none of these were anomalous results, we would then take a mean or an average of these results and then use this to calculate the resistance. This just allows us to remove any anomalies and give us a more accurate result. Then we need to look at the part of the question where they ask us to include a risk assessment for one hazard. So when they ask for a risk assessment, they want us to identify the hazard. We need to identify the risks that this could cause and then identify how we are going to avoid it. A risk in this experiment is that the wire could overheat, and this could happen if we use very large currents. So what could happen if we allow this to take place is that the person doing the experiment could get burnt, which is a risk. And then how we're going to avoid this happening is by using a low current throughout the experiment. After we've taken repeat readings for both the current and the voltage, and then calculated a resistance for each length of wire, we then need to plot resistance against length. Why would switching off the circuit between readings have improved the accuracy of the student's investigation? Tick 1 box. This is a 1-mark question, we just need to select one of the answers. So in this experiment, we are calculating how the resistance of our wire changes according to how we change length. So that means we have 2 of these variables, the independent variable and the dependent variable. Along with this, we also have control variables. These are things that we need to keep the same in order for us to be able to fully see how length affects resistance. So one of these is the temperature of the wire. And we need to control this because when the temperature of the wire increases, this causes an increase in resistance. So what we need to do is to try and control this temperature, to try and keep the temperature of the wire constant throughout our experiment. So the way we can do this is by switching the circuit off between readings. This is because when we switch the circuit off, this causes the current to stop and gives the wire a chance to cool down. therefore controlling temperature. Therefore, the answer that most correctly describes why we disconnect the wires between readings is the last answer. The temperature of the wire would not change if we disconnected the wires. The student uses crocodile clips to make connections to the wire. They could have used a piece of equipment called a jockey. Figure 4 shows a crocodile clip and a jockey in contact with a wire. How could using the jockey have affected the accuracy and resolution of the student's results compared to using the crocodile clips? So in order to answer this question, I think first it would be good to understand the definition of both accuracy and resolution. So accuracy is how close is the value that we've measured to the true value. And the resolution of the measurement is what's the smallest change, for example, in this experiment with length, that I could measure using this equipment. So when we're looking at accuracy, which is the first three options of this question, we're given the choices: the accuracy would be higher, the accuracy would be lower, and the accuracy would be the same. So let's look at what we have here. So the accuracy is how close is my value to the true length of the wire. Now we can say that the jockey, so the second measurement, that's going to give a value closer to the true length of the wire, because you can see that the tip here of this measuring device is much smaller than the crocodile clip. This gives us a much more accurate reading, which means a reading that's closer to the true value. Therefore, we can say the result is more accurate. Then looking at resolution, so the smallest change in length that could be measured. If we think about the resolution with the crocodile clip, the resolution is lower for this way of measuring the length. And this is because, again, we have a wider base, and therefore the ability to change the length and measure this is reduced. Therefore, with the jockey, we have an increased resolution. Therefore, it is this option. The resolution of the length measurement would be higher. Figure 1 shows a cyclist riding along a straight, level road at a constant speed. Complete the sentences. As the cyclist rides along the road, the something energy store in the cyclist's body decreases. So we're looking for an energy store in the cyclist that is going down. So what's happening when this man is cycling is that energy is being transferred from his body. He is pushing on the pedals, and work is being done against the air resistance on the bike, against the friction between the floor and the wheels. And it's also being transferred to the kinetic energy store of the bike, which is increasing until the bike is travelling at that constant speed. So what's happening is energy is being transferred from the man's body. But what energy store is this in his body? So when his muscles are doing work, he's pushing against the pedals, and that's increasing the kinetic energy of the bike. What's happening is it's the chemical energy in his body that is decreasing, and this energy is being transferred from the chemical energy store into the kinetic energy store of the bike. So that chemical energy is there due to the food that he eats, for example, and that is transferred to kinetic energy. So therefore our answer to this is the chemical energy store of the bike user decreases. The next part, the next sentence, the speed of the cyclist is constant when the work done by the cyclist is something to the work done against air resistance. So here they're asking, what is the relationship between the work done by the cyclist and the work done against resistance when the speed is constant? So we've been told above in the first sentence that the cyclist is riding along a straight level road at constant speed. Because their direction is therefore not changing, that means that their velocity is constant. And what we know when velocity is constant is that their acceleration equals 0, because acceleration equals change in velocity over time. If there's no change in velocity, then it equals 0. What we also know about acceleration is that this means that the resultant force on the cyclist equals 0. It means the forces on the cyclist are balanced. And we know that work done equals force multiplied by distance. Work done by air resistance also equals force times distance. Now the distance for both of these forces are the same because the bike will travel a certain distance. Therefore, we know that the forces must be the same for the resultant force to be 0. Therefore, the work done by the cyclist and the work done against air resistance has to be the same, because the work done must be the same if both the force and the distance of these two are the same. Therefore, our answer to this is that the work done by the cyclist is equal to the work done by against air resistance. Figure 6 shows how the speed changes as the power output of the cyclist changes. So first, write down the equation that links power, time and work done. So this is just something that you need to learn, and what they want us to write here is that power equals work done divided by time. You could also write this, if you wanted to, as P equals W over T. Calculate the work done by the cyclist when his power output is 200 watts for 1,800 seconds. So, above we've already worked out the power formula, which is P equals W over T. What we need to do is rearrange this so that W is the subject, because they want us to calculate work done. Therefore, we times both sides by T in order to do this, and we get W equals PT. W equals power times time. And this is the first mark we get for rearranging this equation. The second mark is then for inputting the values that they've given us into this equation. So P is 200 and T equals 1,800. That gives us our second mark. And then our final mark is for the final correct answer, and that is 360,000 joules. That is our final mark, and then just put that in the answer box. So for this question they didn't need us to write the unit, but just always be careful because sometimes they will ask you to also add the unit, and that will be an extra mark. But our third mark here just comes from the final answer. Calculate the percentage increase in speed of the cyclist when the power output changes from 200 watts to 300 watts. So for this, what we're going to need to do is look at the graph that they've given us above, and we need to look at the speed difference from 200 watts to 300 watts. Start from 200 and we go up to the line, and then we go across to the y-axis. We can see here that the speed at 200 watts is 9.5 meters per second. Then we do the same for 300 watts. So starting at 300 on the y-axis, going up to the line and going from the line to the y-axis, what we have is a speed of 11. So what we can see is our change in speed is from 9.5 meters per second to 11. So if we just note that down so we remember that, so at 200 watts the speed is 9.5 meters per second, and at 300 watts the speed is 11 meters per second. So when we're doing percentage increases or percentage decreases, what we need to do is the change over original value multiplied by 100 to give us a percentage. So we get the first mark from working out the change in speed, and so if we just do that here, we do that by doing 11 minus 9.5, And this calculation here, working out that change, is our first mark. And then our final mark comes from putting in the original value, which was the speed when the power was 200 watts, and that is 9.5, and multiplying that by 100. And what that gives us is 15.8%. And that is the final mark, the second mark there. The maximum speed this cyclist can travel on a level road is 14 meters per second. How does cycling uphill affect the maximum speed of the cyclist? Explain your answer. So an explain question means we need to first say how does cycling uphill affect it, just a simple statement, and then we need to unpick that and explain why we have given this answer. So let's think about the situation we have here. We have a level road is our first situation, and then we have a uphill incline that the cyclist needs to go up. So what is different between these two scenarios? And what is different basically is that in the first situation there's no change in height, whereas in the second situation we have a change in height. And when you see this, straight away what we should be thinking is that this change in height means that there is a change in gravitational potential energy. So if you think that equals mgh, so if we have a change in height, then that means we're either gaining or losing gravitational energy. And as we're going upwards, work is being done against gravity. This means that the gravitational potential energy of the cyclist is going to increase. However, this doesn't happen. There is no change in GPE, and so no energy is transferred to the gravitational potential energy store of the cyclist. The power input is the same. The cyclist is pedaling, and they are transferring the same amount of chemical energy into this process. So what's going to happen is that the maximum speed is actually going to decrease, because the maximum speed depends on how much of the energy that we put in is transferred into kinetic energy. And if the energy that we put in, that's going to stay the same. However, in the second scenario here, where we have an incline, this goes to the kinetic energy, or the EK, of the cyclist, but also to their gravitational potential energy. And there are also resistive forces like air resistance that they have to work against. So if the energy in is going to stay the same, this means that the EK is going to have to decrease. So therefore, the maximum speed of the cyclist is going to decrease. And this is our first mark. Our next two marks then come from explaining why this is the case. So what happens is that our power input is the same. Our power input does not change. However, as work is done against gravity, this means that the maximum speed of the cyclist must decrease. And this is our second mark. And saying that work is done against gravity is our final mark. And then just to tie it all together, we just refer back to the question, work is done against gravity, so the maximum speed must decrease. Complete the sentence, choose answers from the box. The current through an ohmic conductor is directly proportional to the something across the component, provided that the something remains constant. So for the first part of this sentence, the current through an ohmic conductor is directly proportional to what? So this is a question asking us about Ohm's law. So An ohmic conductor is a conductor that follows Ohm's law. And Ohm's law states that the resistance of a component is constant even when its current or potential difference is changing, provided that the temperature of the component remains constant. So this is a law that we need to remember, and our understanding of this allows us to answer the question. So Ohm's law is that the resistance stays constant, and the graph for an ohmic conductor looks like this. You have resistance as the inverse of your gradient, so you have an IV graph, current here and voltage here. The graph looks like a straight line through the origin. And so what we can tell about when we have two variables and the points that they make plot a straight line through the origin is that these two variables are directly proportional. So here we have voltage and current plotted on a graph, and they're asking us what is the current directly proportional to, and our answer to this is right here, is voltage, which one of the answers is potential difference. And then the second part of Ohm's law is that this is only true provided that the temperature remains constant. This is because, for example, if our temperature increases, then the resistance of our component will increase, because an increase in temperature causes an increase in resistance. So therefore, our resistance would not be constant. Therefore, the final part of this statement is provided that the temperature remains constant. And those are the 2 marks for that question. Figure 7 shows a current potential difference graph for a filament lamp. Explain how the resistance of a filament lamp changes as the potential difference across it increases. So it's a 3-mark explain question. First, we need to state how the potential difference affects the resistance, and we also need to say why this happens, give 2 points as to why this happens, and develop this answer. So our first point, which is going to lead to our final answer, is to discuss how the current changes as potential difference increases. And they've given us a graph, so we need to use it. We can see that as potential difference increases along the x-axis, you can see that our value of current also increases as well. So our first point is to state that from looking at the graph, we've seen that as potential difference increases, the current increases. And this is our first mark. What we then need to do is start linking this to resistance. And what we need to know about current is that when a current flows, this is the flow of electrons, this electrical energy, some of it is transferred to the thermal energy of the filament lamp, of the wire in that lamp. So as current increases, the temperature of the lamp also increases. This is our second mark. And then for our final mark, we need to link it to the main point of the question, which is how does the resistance then change? So if our temperature is increasing, an increasing temperature means that the particles in the wire, so that's both the positive ions that make up the wire and the electrons that are flowing through the wire, they have more energy. So if our temperature is increasing, so they oscillate more, they vibrate more, which means there are more collisions between them, and therefore the resistance of the wire increases because it's harder for a current to flow. Our final point is that the resistance of the filament lamp increases as potential difference increases. Many householders are replacing their filament lamps with LED lamps, which are more energy efficient. What does more energy efficient mean? So firstly, the definition of efficiency is the proportion of the total energy inputted that is outputted as useful energy. For example, if we were talking about a light bulb, the useful output energy would be the light energy, and then the total input energy would be the energy that it gains from the mains electrical power supply, and then non-useful energy, so energy that's wasted, would be things like sound energy and heat energy. So when we're talking about something being more energy efficient, we mean that a higher proportion of the total energy inputted is outputted as useful energy. A light-dependent resistor is used to turn on an outside lamp when it gets dark. Part of the circuit is shown in figure 8, so we can see figure 8 here. The light intensity decreases. What happens to the potential difference across the LDR and the current in the LDR? So this is something that we need to learn, that for a light-dependent resistor, when the light intensity goes down, this means that the resistance of the LDR increases. So the resistance increases when this happens. So you just need to know that. And then we need to know, because we're asked what is the potential difference and what is the current. We know that the resistance is going to increase, and so we want an equation that ties all these three things together. You know that R equals V over I. What we can then use this equation for is to decide whether resistance and voltage and resistance and current are inversely proportional or proportional. So if they're proportional, that means that as the resistance increases, then this variable will increase. So, as we can see, by using this equation, R is proportional to V. And because I, current, is on this side of the fraction, it's a denominator on the fraction, we can see that R is inversely proportional to I. So that's a 1 over I. So now we know that the resistance is going to increase. We can then use these two statements that I've written here, that resistance is proportional to voltage but inversely proportional to current, and that's going to tell us what is going to happen. So resistance increases, therefore potential difference will do the same because they're proportional. Therefore potential difference will increase. However, if resistance increases, because they are inversely proportional, the current will do the opposite thing, which is to decrease. So the potential difference increases, whereas the current decreases. What is the resistance of the LDR when the potential difference across it is 4 volts? Give a reason for your answer. So for this, we need to go up to the diagram that they've given us, and they've told us that potential difference across the LDR is 4 volts. So if, for example, if we had a voltmeter here, that would read 4 volts. And because we have a series circuit, the total voltage of 12 volts needs to be shared between these two components. Therefore, the voltage across this resistor is going to be 12 minus 4, which equals 8 volts. And what we've already worked out is that the resistance and the voltage are proportional to each other. So if this component here has 8 volts across it and a resistance of 2000 ohms, what we've done to get from 8 volts to 4 volts is divided by 2. If we go back down to the question, we have a resistor which is at 8 volts and has a resistance of 2000 ohms, and we then have a LDR with a potential difference of 4 volts, and we want to know what the resistance is. Because they are directly proportional, if this is divided by 2, then we just do the same to the resistance. We divide by 2. 2000 divided by 2 is 1000 ohms. That's our first mark. And then for the second mark, what we need to do is to describe why, which is what I've just discussed. And that is that the potential difference is shared in proportion with the resistance. Calculate the current through the LDR when the resistance of the LDR is 5,000 ohms. Give your answer to two significant figures. So for this equation, we're going to use V equals IR for the whole circuit. So for that, we need to know V and R for the whole circuit. So R with series in with resistors in series, we add them up. So we already have a fixed resistor of 2,000 ohms, which you can see in the figure above, and then we have the LDR, which has a resistance of 5,000 ohms. And then we know the voltage is 12 volts because that is the voltage of the battery pack. So if we substitute the values that we've just worked out, V equals IR, we have 12 equals I times 7,000. And that is our first mark for recognising those two values. Then need to do is rearrange this, so we have I equals, and we take 7,000 over to the other side, 12 divided by 7,000, and this gives us a value of 1.71 times 10 to the minus 3 amps. So we get the second mark in this question for rearranging, and we get the third mark for getting the correct answer of 1.7 times 10 to the minus 3 amps. So the final mark that we get is rounding this to two significant figures, and 1.71, two significant figures, rounds to 1.7 times 10 to the minus 3, and they've already given us the units, and that is our fourth mark in this question. Smoke alarms contain an alpha radiation source and a radiation detector. Figure 9 shows part of the inside of a smoke alarm. The smoke alarm stays off while alpha radiation reaches the detector. Why does the alarm switch on when smoke particles enter the plastic casing? So what's happening here is we have a source of alpha radiation and then a detector here. And the alpha radiation is travelling from the source to the detector. And when there's no smoke, the count rate on the detector is high enough, so the alarm does not sound. However, what happens when we have smoke is that this interferes with the radiation. This means that the alpha radiation is absorbed by the smoke particles, and therefore not enough alpha radiation reaches the detector for the count rate to stay high enough for the alarm circuit to not sound. Therefore, the alarm will switch on because the count rate has decreased to a certain level. Therefore, our answer for 1 mark is to say that the alpha radiation is absorbed by the smoke particles. Why is it safe to use a source of alpha radiation in a house? So this question is testing our knowledge of the properties of different types of radiation, and usually when they're asking us about properties, they're asking us about the range of this radiation or how penetrating it is. And to answer this question, we could use our knowledge of both of these properties. So for alpha radiation, its range is very short, it's only a few centimetres in air. And how penetrating, it is only weakly penetrating. It's the radiation that we need to know at GCSE that it's the weakest at penetrating substances. So our knowledge of both of these things allows us to answer this question, because firstly, if we were to talk about the range, we could say that alpha radiation has only a short range, therefore it won't travel very far away from the smoke detector in order to harm people. Or we could talk about how penetrating it is, and we could say that it does not penetrate human skin and therefore cannot be of harm to us. So using either of these would get you the mark, but I will just talk about the fact that it has a short range in air, therefore cannot reach humans in the house to harm them. The smoke alarm would not work with a radiation source that emits beta or gamma radiation. Explain why. So the whole reason that the smoke alarm works is that the alpha particles are absorbed by the smoke particles. And the property of alpha radiation that allows this to happen is that it does not penetrate very far. So it's easily absorbed by the smoke. However, we need to know about the properties of beta and gamma radiation. Now they will penetrate a lot further, and while, for example, a piece of paper would absorb alpha radiation, it will not absorb beta or gamma radiation. So therefore, our first point needs to be that the beta or gamma radiation would be able to penetrate the smoke. Our second point is then to say, why would this mean that the smoke alarm would not work? And the reason for this is that the smoke alarm works on the basis that the count rate decreases when there is smoke present, and this causes the alarm to go off and tells the people in the house that there is smoke. However, because the beta and gamma radiation can penetrate the smoke and it's not affected when there are smoke particles, the count rate will just stay the same. So the count rate will not change enough for the alarm to switch on, and that is our second point. Figure 10 shows how the count rate detected from the radiation source in the smoke alarm changes with time. The smoke alarm switches on when the count rate falls to 80 counts per second. Explain why the radiation source inside the smoke alarm should have a long half-life. So this is a 2-mark question, and our first mark will come from getting data from this graph that they've given us. And then our second mark will come from explaining why the smoke alarm should have a long half-life. So the data that they've given us is that the alarm switches on when the count rate falls to 80 counts per second. So on the y-axis, if we find 80 counts per second and move across to the line, and then find the corresponding point on the x-axis. And we can see that this is at 1.123 half-lives. This means that once the alpha radiation has gone through 1.3 half-lives, the count rate will be below 80. And we need to mention this in our answer to show that we've understood the graph. And this is our first mark. And then our second mark comes from explaining that if our sample, our radioactive sample, had a very short half-life, this would mean that our count rate would decrease really rapidly, and then the smoke alarm would basically just go off all the time. So if you think, if, for example, it had a half-life of a day, by the time that it had gone through 1.3 half-lives, that's about 1.3 days, then the count rate will already be below 80, and this means that the alarm will go off. So you'd have a smoke alarm that was going off about every 1.3 days, even though there was no smoke. However, if we had a sample with a really long half-life, then because it's decaying so slowly, our count rate stays approximately the same. And this means that when there actually is smoke detected, then the count rate falls and the smoke alarm can go off. So our second mark comes from saying that a long half-life would mean that we would have a almost constant count rate, or by saying, flipping it the other way, saying that a short half-life would mean that the count rate decreased very quickly. Figure 11 shows a patient who has been injected with a radioactive source for medical diagnosis. And here we can see them being scanned after being injected with this radioactive source. Explain the ideal properties of a radioactive source for use in medical diagnosis. So, when we're talking about the properties of a radioactive source, the things that we want to focus on are these. So we want to look at the half-life of the source, and what would the ideal half-life be? To get these full 4 marks, we need to discuss the half-life and then say, why is this the ideal half-life? We also need to talk about the penetrating power, and again, why this is the ideal penetrating power. And then thirdly, we need to discuss the ionizing power of this source. First, let's discuss half-life. What sort of half-life do we want a source to have if it's being used in medical diagnosis? So what we want is for the source to enter the patient's body, for it then to decay, to travel around the body and decay, and then to be able to be detected by the radioactive detector that they have showed us in figure 11. So what we want for a source that's being used in medical diagnosis is for it to have a short half-life. And this is because we want the source to decay and be able to be detected within a few hours. We don't want the patient to have to wait for days and days, and we don't want the radiation to be in their body for days and days. So if it has a short half-life, this means that it reduces the damage that is done to their body, and also means that it can be detected within a few hours by the radiation detector. And so for this we get 1 or 2 marks. It's a bit harder to mark with the 4-mark question because they also want it to be very logically written. So this gives us 1 mark here. And then secondly, if we look at the penetrating power that we want our source to have. So we want our source to be highly penetrating. And this is because we need this source to be able to get out of the human body. For example, if we used alpha, which is very lowly penetrating, then this would not escape the human body, and therefore we'd be able to detect nothing or only very, very low levels of radiation. And this doesn't tell us anything in terms of medical diagnosis. So we need a source that is penetrating enough to escape the skin once it's been inside the human body, so that it can then be detected by the radiation detector. So finally, about the ionizing power. We want the radioactive source to have a low ionizing power, and this is because if a source is more ionizing, then this means that it will knock more electrons off the atoms of the cells of the patient. And when you ionize these cells, what this causes often is cancers, because the cells start to grow really strangely, or tumours, and obviously this is bad, so we don't want this to happen. So instead we want the radioactive source to have low ionizing power in order to reduce damage to the patient's cells. So we get our 2nd mark here, our 3rd mark here, and our 4th mark kind of comes both from explaining each of these points, but also from phrasing this in a logical and complete way. A student investigated how the pressure exerted by a gas varied with the volume of the gas. Figure 12 shows the equipment the student used. A pump was used to compress the gas in a tube. As the volume of the gas decreases, the pressure of the gas increases. So in this case, the student only recorded 1 set of results. Give 2 reasons why taking repeat readings could provide more accurate data. We have the student who initially has only taken 1 set of results, and they want us to explain why doing a different method, which would be taking repeat readings, would provide more accurate data. So when we have only 1 set of results, there could be random errors that are occurring. So for example, something could go wrong with the pump, it could disconnect and we haven't realised, and so our pressure reading is completely wrong. However, if we don't have repeat readings, then we can't tell that this is an anomalous result. So the first reason why we would take repeat readings is in order to be able to remove anomalies when we recognise them. So if you think about it, if we have just 1 reading for 1 volume of gas, then we don't know if this is kind of correct, if this is the sort of trend that our data should be showing. However, if we had 3 pressure readings for this 1 volume of gas, and one of them is completely different to the other 2, then we could say that is an anomalous result and we could remove it. Our first point is that taking repeat readings allows us to remove anomalies. Our second point is then to say that with these readings, once we've removed all anomalies, we can then calculate a mean. And calculating a mean gives us much more accurate data, Another point that we could also have that would give us the mark is that this process of taking repeat readings reduces the effect of random errors. But for the second point, I will put that this allows us to calculate a mean. Figure 13 shows the position of the student's eye when taking volume measurements. Explain what type of error would be caused if the student's eye was not in line with the level of the liquid in the tube. The two sorts of errors that we can have in experiments are random errors and systematic errors. And to answer this question, we need to understand the difference between the two and therefore which error would be caused. So random error is when the measured value is incorrect, so that is different to the true value by an unpredictable and different amount each time. However, systematic error is when the measurement is different to the true value by exactly the same amount each time. So what we have with this situation here is that our question is saying the student's eye is not in line with the level of the liquid. That means the student could be reading the level of the liquid from here, they could be reading it from here, they could be reading it from here. So every time it's going to be different. And what that means is that this error is a random error. Because every time, for example, if they take a measurement from here, then the difference from the true value will be different to if they take a measurement from here. So there will be an unpredictable difference between the true value and the different measured values. So our first mark comes from saying that this would cause a random error. And our second mark comes from saying that this is because the level at which the student reads the volume will be different each time. Like I've drawn with purple lines, it will be different. For example, one time it could be this first one, the next time it could be reading below the line, and so it's unpredictable. The student will have a different position every time relative to the liquid. If a gas is compressed too quickly, the temperature of the gas increases. Explain how the temperature increase would affect the pressure exerted by the gas. This is a 2-mark question. Our first point needs to be how does the pressure change? And then our second point needs to be explaining why. So when we have a temperature increase, what happens is that the kinetic energy, or the EK, of the particles increases. This is because they gain energy. Higher temperature means there is more energy. And when they have more kinetic energy, that means their velocity increases. So this means that when they collide with the walls of the container, which is what pressure is, that they do this with a higher force and more frequently. And we know that pressure equals force over area. So when the force that these particles are exerting on the walls of the container increases, this means that the pressure also increases. So velocity increases, force on the wall. Therefore, we can see from this that when our temperature increases, this means that the pressure increases. And because it's the 2-mark question, we don't need to go too much in depth about why. The only thing that is required for the second mark is to say that the pressure increases because the particles have a higher kinetic energy. One of the students' results is given below. Pressure equals 1.6 times 10 to the 5 pascals, and volume equals 9 centimeters cubed. Calculate the volume of the gas when the pressure was 1.8 times 10 to the 5 pascals. The temperature of the gas was constant. To work this out, what we need to do is use a formula that is on the data sheet, and that is that PV equals constant. That means that pressure times by volume for a gas is a constant, and we use this to work out what the volume of the gas was. So if we rewrite this as P1 V1, so this is our initial pressure and our initial volume, equals a constant which we'll call K. And we also know that P2 V2, so that's our second pressure that they've given us, 1.8 times 10 to the 5, and then the volume that they want us to work out, also equals a constant. What we can do, because these two things equal the same thing, is we can equate them. So P1 V1 equals P2 V2. And then all we need to do is substitute in the values that they have given us. So our P1, our initial pressure, what they've given us, is 1.6 times 10 to the 5. We multiply that by V1, which is 9 centimetres cubed. And just note that although they've given it to us in centimetres cubed, and normally volume should be in metres cubed, because they've asked for our answer in centimetres cubed, we don't need to convert. So 1.6 times 10 to the 5 times 9. What we need to do then is divide that by P2, because we're bringing this over to this side of the equation, divided by 1.8 times 10 to the 5. And so we get 2 points for these steps for both recognising that these two can be equated and then for substituting our values in. And therefore for V2, what we get is 8.0 centimetres cubed. And it's important to write this to two significant figures because all of the values that they've given to us have been in two significant figures. Therefore our volume is 8.0 centimetres cubed. Figure 14 shows a person using a bicycle pump to inflate a tyre. The internal energy of the air increases as the tyre is inflated. Explain why. So the internal energy of a gas, or a liquid, or a solid. So the internal energy is defined as the sum of the kinetic energy, so the EK, and the potential energy, so the EP, of all the particles of the substance that we have. So in this case, this is the sum of the kinetic energy and the potential energy of the air in the tyre. So when they're asking why the internal energy increases, what we want to focus on is the kinetic energy of the particles. And for this question, what we want to focus on is this process in terms of energy transfers. So what the man here is doing is transferring energy to the air in the tyre. He's doing work on the air in the tyre because some of the chemical energy from his body is doing work, he's pushing down on the pump, is being transferred to the kinetic energy store of the particles. So our first point comes from saying and noticing that work is done on the air that is in the tyre. Our first mark. And then we need to link this to why the internal energy increases. So if work is done on the tyre, we have transfer energy. We've transferred energy from the chemical energy store of the man to the kinetic energy store of the air molecules in the tyre. What's happening is that their temperature is increasing, and this causes the increase in internal energy. And this is our second mark, this is all we need to write. However, just to tie it all together, we can add on the end, so the kinetic energy increases, and so the internal energy increases. But all we need is those 2 points with red ticks for those 2 marks. Nuclear power stations generate electricity through nuclear fission. Electricity can also be generated by burning shale gas. Shale gas is a natural gas trapped in rocks. Shale gas can be extracted by a process called fracking. There is some evidence that fracking causes minor earthquakes. Burning shale gas adds carbon dioxide to the atmosphere. Describe the advantages of nuclear power compared with the use of shale gas to generate electricity. This is a 3-mark question, and we don't actually need to know anything about shale gas because they've given us all the information here, and it's really important that we use the information that they have given us here. So we're looking at the advantages of nuclear power, so what we want to find in these 2 sentences that they've given us are disadvantages of shale gas. So shale gas requires fracking, which causes minor earthquakes, and burning shale gas also adds carbon dioxide to the atmosphere. So those are two negatives, and that is enough for the 3 marks as long as we compare those to the advantages of nuclear power. So we know that there's no CO2 emitted with nuclear power, and then we need to explore why is this an advantage, or why is it good that there's no CO2 emitted. And we know that CO2 is a greenhouse gas, and so this causes the greenhouse effect, and one of the effects that the greenhouse effect has is of global warming, which is obviously a negative. And then we can compare the fact that we know that nuclear power is less destructive to the environment. Although we do have radioactive waste, what we don't have are earthquakes. So we can mention this, and that will be our 3rd mark. So you can see it's quite simple to extract the information from the paragraph. You don't need to know anything about shale gas and compare that to what we do know already about nuclear power. So our 1st mark will come from saying that nuclear power does not require any CO2 to be emitted, whereas shale gas does. And then secondly, that this is positive because it does not cause global warming. Our 2nd point is to say that nuclear power is less destructive to the environment because it does not cause minor earthquakes. That would get us all 3 marks. What is the name of one fuel used in nuclear power stations? For this, we just need to know the names of fuels that can be used, and we can have either uranium or plutonium. They're both fuels that are used in nuclear power stations, and to get that 1 mark, either one of them can be used, but I will just say uranium. And although, for example, you might know that it's uranium-235 that is often used, you don't need to mention any numbers, and these will just be ignored. All you need is to mention uranium or plutonium. Describe the process of nuclear fission. I think the easiest way to understand nuclear fission, and then to get all 4 marks on this question, is to draw a simple diagram that shows what happens during nuclear fission. So during the process of nuclear fission, what happens is that a slow-moving neutron is absorbed by a large and unstable nucleus. This large nucleus then splits into 2 lighter nuclei, which are more stable. As well as this, 2 or 3 neutrons are emitted, and energy is also emitted in the form of gamma radiation. So for this 4 marks, all we need to do is describe this diagram that I've drawn here. So firstly, what we have is a neutron being absorbed by a large and unstable nucleus. We then get our next and final 3 marks by explaining what the products of this reaction are. So firstly, we need to say how there are 2 lighter nuclei that are formed, and how there are 3 or 2 neutrons that are also emitted, and finally that we have energy that is released. Figure 15 shows a coffee machine. The coffee machine uses an electric element to heat water. The coffee machine has a metal case. Why would it be dangerous for the live wire of the electric cable to touch the metal case? So the live wire is the brown wire in a plug, and what this does is it has a very high potential difference of 230 volts that it carries from the mains, and this allows electricity to flow. However, if it touches the metal case, what happens is that our metal case becomes live and is at 230 volts. So if we have a person who is grounded, they're at 0 volts, we have a massive potential difference between the metal case and the person. And what happens when we have a massive potential difference is that a current can flow. And this very large flow of current is what we would call an electric shock. Therefore, the danger of the live wire touching the metal case is that there is a risk that the person touching it could get an electric shock. The power output of the coffee machine is 2.53 kilowatts. The mains potential difference is 230 volts. Calculate the current in the coffee machine. For this question, we need the equation P equals IV, power equals current times voltage. So our first mark comes from substituting the values into this equation. And also we need to notice that because we are given the power in kilowatts, we need to convert this into watts. So kilowatts, 1 kilowatt equals 1000 watts. Therefore 2.53 kilowatts equals 2530 watts. So for our first mark, P equals IV, we need to substitute in 2530 equals current, which is I, which we want to find out, multiplied by 230. This gives us our first mark. Then get our second mark for rearranging this so that I is the subject. That's 2530 divided by 230, because we divide both sides by 230 for our second mark. And then for our final mark, put this into the calculator, and this gives us I equals 11 amps. So we just get our final mark for this final answer of 11. The coffee machine heats water from 20 degrees Celsius to 90 degrees Celsius. The power output of the coffee machine is 2.53 kilowatts. The specific heat capacity of water is 4,200 joules per kilogram degrees Celsius. Calculate the mass of water that the coffee machine can heat in 14 seconds. So for this question, as soon as you see specific heat capacity, we should be thinking of the specific heat capacity equation, which is on the data sheet. And this is that the change in energy of a substance equals its mass times its specific heat capacity, which is C, times by its change in temperature, delta theta. And then what we can also see is that we have been given power, and we've also been given time. But we haven't been given energy, which is one of the variables that we need for this equation. So, and another equation that we need that is not on the data sheet is P equals E over T, because that ties together the two variables that they've given us, which are P and T, and that final variable that we need, which is E. So, our first equation comes from finding delta E, the change in energy. And we use P equals E over T for that. So if P equals E over T, we can rearrange that, times both sides by T, and we get E equals PT. We then substitute in the values that they've given us for P and T. Therefore E equals 2,530, remembering again, like we did in the previous part of the question, to multiply this by 1,000 to get it in watts. And then multiply by T, which is 14. Put that into your calculator. And we get 35,420 joules. Then what we need to do is use the rest of the values that they've given us, as well as the specific heat capacity equation, and in order to complete this question. So we get 2 marks for this final answer of our energy, and for recognising that we need to use P equals ET. Then get our 3rd mark for using the specific heat capacity equation. So we've worked out that delta E, the change in energy, equals 35,420, and then we need to use the values that they've given us. So we don't know M, that's what we're trying to find out. Multiply this by C, the specific heat capacity, which is 4,200, and multiply this by the change in temperature. So we've gone from 20 degrees Celsius to 90, so our change in temperature is 90 minus 20. We get our 3rd mark for this, and then we're going to get our 4th mark for rearranging this so that M is the subject. So if we want M to be the subject, what we need to do is take these values and divide 35,420 by these values. So M equals 35,420 divided by 4,200 times 90 minus 20, which is 70. And we get our fourth mark for this rearranging. And then we get our final mark for the final answer. So when we put this into our calculator, we get that m equals 0.12047, etc., etc. It's a reoccurring number, but all we need to do is put this to two significant figures, because the lowest number of significant figures that they've given us in this question is 2. So therefore m equals 0.12 kilograms. They've already given us the unit, so we get our final and fifth mark from stating that the mass therefore equals 0.12 kilograms. Figure 16 shows a wind turbine. At a particular wind speed, a volume of 2.3 times 10 to the 4 meters cubed of air passes the blades each second. The density of air is 1.2 kilograms per meter cubed. Calculate the mass of air passing the blades per second. So for this, we need to use the equation density, which uses the symbol rho, equals mass over volume. And the units for all of these are mass is kilograms, volume is meters cubed, and density is kilogram per meter cubed. So firstly, what we want to do is we're just going to input our values into this equation. So if density equals mass over volume, they have given us volume and they have given us density. We know that 1.2 equals mass over volume, which is 2.3 times 10 to the 4. And then we need to rearrange this, and we do this by multiplying both sides of the equation by 2.3 times 10 to the 4. So we get mass, which is what we're trying to find, equals 1.2 times 2.3 times 10 to the 4. We get a final answer of 27,600 kilograms. So the 3 marks for this question come firstly from inputting the values that they've given us into the density equation. We then get our second mark for rearranging this, and the third and final mark comes from the final answer of 27,600 kilograms. The power output of the turbine is directly proportional to the kinetic energy of the air passing the blades each second. Describe the effect on the power output when the wind speed is halved. So the first thing to notice here is that we're told the power is directly proportional to the kinetic energy of the air. So however much power the turbine outputs, the kinetic energy that the air that passes these blades is proportional to this. So this means that if our power output of the turbine doubles, then the kinetic energy of the air doubles. And if the power halves, for example, then the kinetic energy of the air halves. They change in relation to each other, in proportion to each other. So we're told that our wind speed is halved. In order to connect wind speed to kinetic energy, what we need to remember is the kinetic energy formula. So kinetic energy equals half mv squared. And we need to understand how both the mass and the velocity affect the kinetic energy. Because when our wind speed is halved, so the wind speed is divided by 2 over 2. This has an effect on both the mass and the velocity in our kinetic energy equation. So if we think first about the velocity, if the wind speed is divided by 2, this means that the air that passes the blades each second, its velocity is divided by 2, it's halved. So therefore v is going to be divided by 2. This also has an impact on the mass. So if our wind speed is halved, then only half the mass of air will pass the blade each second, because less air will pass the blade per second as it is moving slower. So mass is also divided by 2. So we know that we've halved both of these variables in our kinetic energy formula. And now we need to look at the relationship between kinetic energy and velocity and kinetic energy and mass to see how these two changing variables affect the kinetic energy. So we can see that the kinetic energy is proportional to mass. However, the kinetic energy is proportional to the velocity squared. So when we're looking at mass, this means that if our mass is doubled, then our kinetic energy doubles. If our mass is divided by 10, then our kinetic energy is divided by 10. However, with velocity, so in the case that we have here, where our velocity is divided by 2, because we have v over 2 squared, this is v squared over 4, the impact on our kinetic energy is that it is actually decreased by a factor of 4. And this is all because the kinetic energy is proportional to the square of the velocity. So we need to mention, to get the first 2 marks, the effect of the changing velocity and the effect of the changing mass on the kinetic energy. So if we mention first the mass, so we've worked out that the mass is halved, and because kinetic energy and mass are proportional, this means that the kinetic energy also decreases by a factor of 2. We then need to talk about how the changing velocity impacts the kinetic energy of the air. And so we've established here that because our velocity is divided by 2, this means that our kinetic energy will decrease by a factor of 2 squared, which is 4. Then to answer this question finally, which is that we need to describe the effect on the power output, we need to say these 2 changes have been made. So our kinetic energy is halved by the mass of the air, and it is quartered or decreased by a factor of 4 by the velocity of the air being halved. So these 2 changes we need to do is just do 2 times by 4, and that equals 8. Because we have the mass of air that decreases our kinetic energy by a factor of 2, and then we have the velocity of the air changing, which decreases the kinetic energy by a factor of 4, and these 2 changes are multiplied, and finally the kinetic energy is decreased by a factor of 8, and therefore because the power is proportional to the kinetic energy, therefore the power decreases by a factor of 8. So our first mark from discussing the effect that the mass has. We get our second mark from discussing the effect that the velocity has on the kinetic energy, and our final mark, our third mark, from mentioning how the kinetic energy therefore decreases overall, and therefore how the power output decreases overall. At a different wind speed, the wind turbine has a power output of 388 kilowatts. The mass of air passing the wind turbine each second is 13,800 kilograms. Calculate the speed of the air passing the blades each second. Assume that the process is 100% efficient. So it's important that they've told us that the process is 100% efficient, because this means that all of the energy produced by the wind turbine will be transferred to the air. Although this wouldn't happen in reality because energy would be lost through things like air resistance, we will assume that this is true for this question. So the equations that we're going to need to use for this question are P equals E over T. P is in watts, T time is in seconds, and energy is in joules. And then to connect this to the speed of the air, we're going to need to use our kinetic energy formula, which is EK equals half mv squared. EK, kinetic energy, is energy, so it's in joules. Mass is in kilograms, and V is in meters per second. Firstly, if we write down what we know, and then what we're going to do is connect these variables using these 2 equations. So we know power, because we know that 100% of the power has been transferred to the air, it's been transferred usefully. So we know that 388,000 watts, remembering that we need to do watts because this is our unit for power, has been transferred, and we know that T equals 1. And we know this because in the question they've told us that the mass of air passing the wind turbine each second is 13,800 kilograms. And so they've told us each second, this means per second, which is every 1 second. Then we know mass, because they've given this to us, this is 13,800 kilograms. And what we're trying to find is the velocity of the air, the speed of the air, which is an unknown. Firstly, we're going to use the equation P equals E over T. We can rearrange this and we get E equals PT. And because t is 1 second, we therefore know that our energy is just 388,000, because 388,000 times 1 is just 388,000. And we then use our kinetic energy formula. So we then use EK equals half mv squared, and we input the values that we already know. So we get 388,000 equals half the mass, which is 13,800, times by the velocity squared. And then we need to rearrange this in order to make v the subject. So if we divide this side by 0.5, that's like timesing it by 2. It's the same process. So 2 times 388,000. And then we divide this side by 13,800. And this gives us v squared. Then we need to do the square root of the whole left side in order to find v. So rearrange this, v equals the square root of 2 times 388,000 divided by 13,800. And what this gives us is that v equals 7.4987, etc. However, we need to put this answer to 3 significant figures, because this is the same number of significant figures we've been given in the values that they've given us in the question. And that is 7.50. So our first mark comes from substituting these values into our kinetic energy formula. Our second mark then comes from rearranging this to get v squared. And then our final and third mark is from getting the answer of 7.50 meters per second.